This meeting is being recorded.
Okay, good afternoon, everyone. Can you guys hear me?
Yes.
Yeah, okay, thanks, great. Okay, so firstly, I think many of you already saw, I just released the design assignment, first design assignment, so first of two. It's focused on the module related to decoder, encoders, kind of just building more complicated stuff from simpler modules and a little bit of arithmetic. There is a P set which I'll also be releasing shortly, probably by tomorrow, which focuses more on the arithmetic side of things. So for instead of eating up the lecture time, as I posted on Piazza, I'll hold a Zoom session after a 10-minute break after this lecture. It will be recorded, so you don't need to be there. You can always refer to that recording, but absolutely feel free to come by and basically just go over what the different problems in the design assignment are asking for, and also a few Logisim related tips. Okay. The lecture itself, so we are going to pick up where we left off. So last time around, we kind of started on sequential circuits in that short lecture just before the quiz on Monday. We talked about that how we saw that RS latch, which was a sequential circuit, which had state, as in if you kind of go back, it kind of looked like this, and it allowed for it kind of remembered which button was last pressed. And the key thing out here is because of the feedback, the value Q out here depends not only on S and R, but also the previous value of Q. And so that's kind of like the state. But I also mentioned that kind of in practice, we go with what are called as synchronous sequential circuits. In other words, the state, the memory of the system is updated only at some specific instance of time. It's the clock of some sorts, and whenever that clock has a particular instant, that's when things get done. And this was the slide which we had started on. So kind of a usually in clock synchronous circuits, what happens is, so the clock itself is nothing but another digital signal, except one which oscillates between 0 and 1 at some frequency or at some period. It's kind of, as you can see out here. And then we define, in most cases, we define the instant in terms of an edge of the clock. So typically we may say, I'm interested in the positive edge or rising edge of the clock going from 0 to 1, this edge, for example. And then what happens is that within the circuit, whenever the rising edge of the clock comes, at that instant, whatever is present in this next state value, right? If you recall last time we talked about that, how this combination logic takes the input from the outside world, produces the input to the outside world, but it also takes the current state, whatever is in the memory, as an additional input, and it produces what should be the next state, what needs to be written into the memory as its output, right? So this logic is kind of constantly monitoring the outside world and looking at what is in the system's memory, and it's producing what goes to the outside world and what should next go into the memory. The key thing though is, unlike the asynchronous circuits, here the memory is updated only when the clock tick comes. So at the clock tick, we'll examine whatever is the value on this line, and then that gets stored inside the memory. And the output line of the memory always reflects whatever is in the memory. Okay, so just think of it as the wire at the output, the signals at the output are always just following the content of the memory, the state memory. So this is kind of a special storage circuit. It's implemented, as I mentioned in one of the slides last time, using these circuits called flip-flops, but that's irrelevant. Just think of it as a circuit which has this property. Output always reflects the memory, and the memory is written whenever the clock ticks. This symbol that you see out here, the triangle, indicates clocks. So anytime you see a circuit where some input is coming in and there's a triangle next to it, that means that's the clock, and in particular, it's a clock where the rising edge matters. If, on the other hand, the falling edge was important, then you will see a symbol like this, little bubble in front of it, just for the negation. Almost all sequential circuits that we design are synchronous. The asynchronous types are done in special cases, but they're super tricky to design, so I don't sort of spend time on that. It's kind of for more advanced purposes. Okay, so what this means is that a sequential system is nothing but kind of two parts. There is a combinational logic part, right? That's a CL. And so maybe it's better to draw it out here. So this is the combination logic. And then there is this memory, right? This is memory. The memory is some n bits, right? So you can think of a state vector with n bits in it. And every clock tick, whatever is present, are actually in our case S bits. So S is the number of bits. So state has S bits, and every time the clock tick comes, whatever is present on these S bits gets stored into the state. And the output always reflects that. Now, it doesn't mean that at every clock tick state has to, that I have some new value. It could be that I'm just repeatedly writing the same thing. That's also possible. So it could be that the new value present out here is the same as what is already in the memory, in which case, of course, there is no effect. The combination logic is taking two inputs. It's taking in, and let's just think of that this is the next state, and this is the current state. Or sometimes we just call it old state, right? Or present state. So what you can really think of this combination logic as really having two parts to it. It's really kind of two functions. There is a function which is the output function, which takes the current state and the input from the world, right? And produces the output going to the world. And then there is a second function which you can think of as a next state function, and which again takes the same current state and input from the world, but this time this function produces the next state, okay, which is kind of going back into that thing. So this obviously is just a nature of this combination logic. There's nothing, I can always decompose it in this particular manner. So conceptually, all synchronous sequential systems look like this, that their functionality, what they do will be defined by these two combination logic functions, the output function and the next state function. So designing a synchronous sequential circuit, as we'll shortly see today, really boils down to designing these two pieces of combination logic. next state function and an output function, right? Next state tells me what state I'm moving to, right? What's the new state, and output tells me what I'm sending to the outside world. Okay, so so our design problem really is then designing two pieces of combinational logic, right? Everything else, the state memory is obviously a very general hardware. The only thing that will change from one sequential to another is what the value of S is, how many bits of memory I have. I mean, simple things it can be as simple as just 1 bit, or it could be like billions of bits, right? Depends on the complexity of the system. Okay, so so now if you think of this, then first thing is what I'm remembering is S bits, right? S is some finite number. So what that means is whatever input I have seen since when the system started, right? All possible histories that I may encounter, I'm really kind of distilling them down into S bits, and S bits can represent 2 to the power S things. So that means that I, with that S bit of state, I can distinguish between 2 to the power S different histories or different pasts, right? I mean, even if my system has been running for millions of years and the clock frequency was gigahertz, so whatever we have encountered, whatever quadrillions of inputs, doesn't matter, right? Because all I am storing is S bits. So every possible history gets mapped to this thing. So obviously, in general, it's a many-to-one mapping, right? Lots of different histories are going to result in the same state. So last time I had talked about an example that if I'm interested in outputting a 1 or 0, depending upon whether I have seen an even number of ones in the input or odd number of ones. In that case, my S was 1. There are just 2 possible histories. I have seen odd number or even number. So all the possible histories just kind of get collapsed into 1 bit of state. So that's one part, right? That these sequential circuits, because S is finite, they can only remember a finite number of possibilities. Okay, and so sequential circuits are often are a form of what you can say are finite state machines. They have finite number of states. The second thing is that if you go back to our combination logic, which I said is really kind of a general statement. So left-hand side is what we have in general, right? That there is next state and output, and next state takes both current state and world input as input and produces the next state, and likewise output takes both the inputs and produces output. But there is a special case of this where output does not depend upon the world input. The output function only takes the current state as an input and doesn't take the input coming from the outside in order to produce output. Now you may say, okay, that sounds weird, right? How can output not depend upon the input? But remember, the input is affecting the next state. And so the effect of any change in input is going to affect my memory, and then that memory will affect the output. So all that is happening is that instead of the input immediately affecting the output, input is going to affect the output with a delay, with at least 1 clock tick delay. There are a variety of reasons for this thing, but foremost is that circuits on the right are kind of better behaved, because if this left one, the more general case, which is referred to as the Mealy machine, Mealy finite state machine, the problem is whenever input changes, let's say there is a glitch on the input, right? Then the output circuit will immediately reflect, in general, will immediately reflect it on the output, and therefore output can be glitchy. Output can change whenever input gets some change of value. The nice thing about the circuit on the right, which is called as Moore machine, right, is that output only changes when the current state changes. And current state changes only when the clock tick comes. So that means that my output changes when the clock tick comes. And so output changes are happening at a predictable time. Of course, because of circuit delays, output will change a little bit after the clock tick. But the point is that outputs are synchronized to the clocks. So in this case, outputs are synchronized. With the clock. And that's a nice thing because our makes debugging easier, right? I don't have to, but more importantly, if there was noise in the environment and therefore in saw some glitch, that will hopefully get ignored. So it results in a more robust system. So our finite state machines can therefore be divided into two categories: mealy, where output is a function of both the current state and the input, and more machines, where output is a function only of the current state. Just bear in mind that other than this timing aspect, right, that output in one case can change at arbitrary times and output in the other case changes at sync with the clock. Whatever functionality you want to do with one, you can do with the other. Okay, so just the only difference really is when the output changes, and we'll see that later in the courses. So one can go back and forth between these two type of machines. Having said that, precisely for reasons of robustness and all that I talked about, this machine is much preferred. So unless you are in the world where output has to immediately reflect the input, it's kind of generally a good idea to stick with mealy machines. Sorry, with more machines. Now, one thing that happens is oftentimes in real world, in real systems, you may have multiple finite state machines, and the output of one finite state machine will become the input to another finite state machine, right? So I may have FSM1, FSM2, FSM3, they may form some sort of a chain. In which case, if the input to a finite state machine is coming from another finite state machine, then once things are synchronized, you are in good shape. And we'll see examples of these systems later, but again, real world systems is not just that decompose into simpler state machines, and then one state machine feeds into another, and that feeds into another, and so on and so forth. But right now, just remember more versus mealy. And more means that output changes only on clock ticks, and therefore output is a function of only the current state, whereas in case of mealy, output is a function of both. Next state clearly has to be a function of both, right? I mean, if next state didn't depend on the current state, then it won't even be state. And if next state didn't depend upon the world input, then the system would never be able to memorize anything about the input it saw, right? So it's only for the output where we have this possibility that either we are looking at state only or state and input. Any questions before I move on? So this concept of state is super critical to understand. Okay, so if not, feel free to interrupt. So mealy versus more, what kind of trade-offs we have? So I kind of already alluded to it a little bit, right? So that more has more robustness to glitches and all in the input, but more has the disadvantage that effect of input will take longer time to reflect on the output. So the next clock tick, right? I mean, so there is a delay, a clock delay that enters into the picture. So it's basically a robustness versus delay kind of a trade-off that occurs. So yeah, I guess this slide goes more into it. So outputs of more change only on clock ticks, and while mealy can change anytime, more therefore is better behaved there because outputs are not affected by the glitches on inputs, but more are slower to react to inputs only at the next clock tick. And it's very important to get this thing kind of right, and we'll, as hopefully in the next second design assignment, you will kind of encounter some of these things, and at the end of the course we'll kind of look at the more nuanced picture on how delays in the combinational logic end up affecting things also. Okay, so now let's look at probably kind of the simplest sequential circuit, like just the state itself, and that is this D flip-flop. Okay, so D flip-flop is is basically a special clocked circuit which lets us store state, one bit of state. So a D flip-flop typically is drawn as shown in the figure on the top right. So it has an input D. Think of D as the data. Output Q, traditionally called Q. So that's okay. And then the clock. And then since in this particular case, you see that clock has only a triangle, no bubble, that means it's the rising edge of the clock. Okay. And that is shown out here. If the clock had a bubble, then that means that the flip-flop is sensitive to the falling edge of the clock. And then what the behavior of the circuit is that Q holds a steady value in the default case. Whenever there is an appropriate edge on the clock, then Q becomes D. So whatever is on D gets captured. So think of it like this thing as memory inside. So at the clock tick, whatever is present on input gets stored out here, and Q always reflects whatever is in the memory out there. Sometimes these things have additional inputs. They have enable, which basically say whether they are listening to the clock or not. So if it has an enable, so like if you look at the flip-flop in Logisim, you would see that it has enable input. Okay, so essentially, if enable is not, if the flip-flop is disabled, then it's not affected by the edges on the clock. Additionally, it may have asynchronous set and reset. Asynchronous set and reset signals, basically, they typically are represented by S and R, and they basically say if I have a asynchronous set, let's say, then whenever that signal is enabled, there's one, let's say, then the content of the flip-flop becomes one, irrespective of the clock. We don't have to wait for the clock. And then there is sometimes also synchronous set and reset, which means that the effect of those signals only takes place at the next clock tick. So you can think of this D flip-flop as the simplest form of memory, something that stores a bit. Now, these are pretty costly. They take lots of transistors. So we use them only in very close to the logic. If you're in the business of storing bulk data, then you would be using your the kind of memories that we talk about in the computer, right? Like DRAMs and SRAMs and perhaps even flash drives and all, right? All of them can potentially create a clock signal, but they're designed for bulk memory storage. The purpose out here is when we are designing circuits where on the chip we need some memory right next to our combination logic. So D flip-flop is how we achieve it. The cost of a D flip-flop is kind of the same order as, let's say, cost of a 1-bit D flip-flop is similar to cost of, let's say, a 1-bit full adder, right? Order of 20 transistors, something like that. Okay, so that's the D flip-flop, very special circuit, very crucial to understand, and let's look at its timing behavior. So, so what you see out here is it's a timing diagram. There's a clock signal, and the flip-flop in our particular case is rising edge sensitive. So the action takes place at the rising edges. Now I have the input D, and what this portion is showing is kind of that I don't know the value of D. It's an unknown value. Okay, so that's what it's saying out here. Okay, unknown. But then at some point at t equal to 1, D becomes 1, right? The outside world is sending us to D becomes 1. But none of this is going to affect Q, or QB stands for Q bar, which, as we talked about last time, it's basically negation of Q. So So that's so when we started out, Q was 0 and Q bar was 1, and then finally there's a signal called reset signal, and reset was high out here, which is why Q was 0 and Q bar was high. Then at t equal to 1, reset goes down to 0. So now we no longer have reset, so the flip-flop basically resumes its behavior. And at that point, let's say also D was 1. Here it was unknown, or I didn't really matter. At the clock edge, the flip-flop will look at D and say, aha, D is 1. And so it will make Q to be 1. So this clock edge together with this value causes Q to become 1 and Q bar to become 0. Now here you see everything happening kind of as if instantaneously, but if you go into a fine time scale, then what is really happening is that Q is going to become 0 to 1 as a result of the clock edge. And so it will happen a little bit after the clock edge. Very tiny amount, hopefully, but a little bit after.
And quick question.
Yeah, go ahead.
So I still don't understand what like Q is Q just the output in this case, and it's just responding to the clock trigger. Okay.
Q is here, right? That's the Q.
What is the point of keeping track of like the negation of Q?
Oh, it's a lot of flip-flops often come both ways, and the reason is that in systems usually we need signal and their negation a lot of times. So oftentimes as practice, what they do is they kind of generate both the signals.
Okay.
So just that.
So in this slide, so when D is 1, is it always matching Q to D every time the clock signal flips?
Clock. So at the clock, whatever is on D gets stored into the flip-flop, and that appears on Q.
Okay, is that just the definition of the flip-flop circuit, or is
that's
it just
okay? That's just the definition, right? Edge on clock changes.
Okay,
Q,
got it.
right? So that's the definition. That's what a flip-flop does. Okay. At a negative edge, nothing happens, and then the next positive edge, since D was unchanged, so nothing happens, right? Because we already had a 1 inside the flip-flop. So at the clock edge, read the D, put it inside the flip-flop, and Q always follows whatever is inside the flip-flop. Okay, and reset overrides everything, right? If reset were to become 1, it will make the flip-flop go back to 0. Okay, so that's how this particular flip-flop behavior is. Like I said, I mean, I may have flip-flops where maybe I don't have QB, maybe I have clock which is sensitive to falling edge, maybe I have set also and not just reset, right? I mean, there are kind of all sort of variants that can exist. So yeah, so we start with unknown data, could be 0 or 1. Then at this clock tick, Q is set to be D and Q bar is set to be not D, and then kind of the whole process continues. So let's look at the next one. Do I have animation here? Yeah. So next time, let's say at this time, remember this is D, right? Sorry, this is clock. I'm sorry. This is D. So, and this is Q, and this is Q bar. So let's say, for whatever reason, D was changed by the outside world to go from 1 to 0. Remember, it had become 1 out here, right? But it's back to 0. But that doesn't have any impact until the next clock tick. So even though there was a clock edge out here, didn't have any impact, right? Q and Q bar remain what they were. But at the next clock tick, next relevant clock tick, rising clock tick, then at this point, it sees, aha, D is 0, and therefore it makes Q to be 0 and Q bar to be 1. And then kind of process continues. So main thing to remember then is that action takes place at rising edge. Any changes in D at other times don't matter. And in fact, if D were, so let's say hypothetically, D were to go high and come back again, none of that will have any effect, right? Because all that matters is the value of D at the clock tick. Okay, so that's how flip-flops work. Okay, so of course, that's one bit. Usually, in general, we'll need to store a bunch of bits, like some S bits, and like I said, S could be very large. So what we really do is we basically would have multiple D flip-flops, all driven by the same clock, and then I will feed my S bits of new state to the corresponding bits of the flip-flop, and the output would be Q. So D and Q are each S bits in some senses. So the symbol is on the right hand side. And once we have something like this, like an S bit of D flip-flops, the term is kind of a multi-bit flip-flop, we often is commonly referred to as register. So register is nothing but bunch of D flip-flops ganged together with a common clock and a common set, reset, and all. It's called a register because it registers something, right? It remembers something. So from the plain English meaning of register. So it's used to store or register values. Okay, that's what's going on. Again, like Logisim has this kind of a module also, right? In a modern system nowadays, you may have like millions and millions of bits worth of state scattered all over a chip. So within Logisim, if you have it handy, you can kind of open it and see. But basically, you would see that there is a clock signal in Logisim, okay, under wiring. And under memory, they have a D flip-flop and they have a register. So all of these things are present in Logisim. And for the clock, you can even set the frequency. So that when you are simulating, you can simulate at a particular rate. Because it is simulating, so it can't really go as fast as real circuits do, but it can go to like kilohertz type frequencies when Logisim runs. Okay, and of course, there are other simulators which let us do similar things. Okay, so we have the D flip-flop. Again, harking back to what we talked about earlier, a sequential system has state. So now we have seen how we can create the state, right? How that circuit looks like. And then it has this combination logic, which we can view as two parts, right? The part which computes the next state and the part which computes the output. So now we are going to see how we deal with that, because that's where the intelligence of a sequential system is. So going back out here to that, so imagine I have a sequential system which has the combination logic and which has the state register. I have just drawn it differently. Previously, I was always drawing the state register to be kind of above the combination logic. This is the same circuit, right? I have input coming from the outside world. There is a clock. There is a state register. There is combination logic. And this combination logic is computing two things. It's computing the output and the next state, right? So when we think of these systems, remember, since they have memory, I can't just talk in terms of what is it now. I have to really examine how it changes over time. So let's say at the current moment, the input at the start, the input coming from the outside world had the value A. A is some n-bit value. And let's say at the start, the state register had stored in it the value SA. SA is some S-bit of value. Now, what this combination logic is going to do is, it is going to compute the next state and the output. So it's basically going to ingest SA and A, and is going to produce some next state. So let's say the next state function, I call it as an F. F is some Boolean logic function which computes the next state. So then the value sitting on the next state wires, the S-bit value, let's call it SB. So I'm going to follow the sequence A, B, C like that. So SB is some function of A and SA, right? A out here and SA out here, we compute, we get the SB. Now, and I'm going to ignore the out, but you can say out is some G of A comma SA. Okay. Then the clock tick will come at some point, right? And at that clock tick, SB gets stored into the flip-flops. And then a little bit after that, so here I have deliberately drawn a little bit of a delay. If I were to observe what is the current state in this wire, we will see SB, right? So what is happening is at the clock tick, the flip-flop captured SB, and a little bit after that clock tick, the state becomes SB. So this is what will happen, right? The state became SB after a little bit after clock tick. And then what will happen is the combinational logic will do its job, and so what will happen potentially at some point is that input also changes, and input B comes, and therefore on the next state wires, right? This next, by the way, is the same as next state out here. Okay, on the next state wire, I'm going to see a new value. So, sorry, let's restart this. Okay, so first one clock tick comes, that computes SB. SB makes it to the output of the register, output of the flip-flops. Then the input changes around that time. And now on the next state, I will get a function of B and SB. Let's call it SC. So SC is a function of B and SB. And that's what you are seeing out here. Then sometime later, another clock tick will come, right? This clock tick. And now as a result, I will see SC on the output. So again, SC appears. And in parallel, the outside world is also messing with the input. So C will appear, and the effect of that would be the new state SD, and so on and so forth. So every clock tick, kind of what is happening is that I'm taking the current value, which the combination logic is taking the current value in state and the value in, and computing the new output, which at the next clock tick reflects onto the state wire out here.
Quick question.
Yeah, go ahead.
So with the clock ticks, like in like both the next and the state categories, why aren't those like exactly lined up with like when the clock has like the upwards tick?
Oh, like when is the state changing? Not
Yeah,
lined
like
up?
why is there some delay between like the
Yeah,
state and the
because
clock
real
tick?
circuits always have delays. So conceptually, you need to think of that when the flip-flop sees the clock, its output changes after a little bit of time, typically very small, nanoseconds or even femtoseconds, but there is a delay. This figure just exaggerates that. Okay, this is to make the point that the changes in state are happening after the clock tick, not because remember there's a cause effect out here. So this is just exaggerating the point that this causes this. Okay, so
and then for the next state, is that also the same thing where like you have the input, you have to wait a while for the next
yeah
state?
so again, so actually this picture is not strictly correct, because what would happen is that as soon as state changed to SC, the next state would begin to change also, right? I mean, sorry, yeah, let me. As soon as the state changes, even if input is stable, next state will begin to change. So if I'm observing the next state will probably begin to change somewhere around out here as a result, right? Because combinational logic also has delays, right? So when next state, when state changes, then even though input is stable, right, input is B, the next state in general can begin to change. But what this figure is showing is that I have the final value of the input changes here, and of that is the it's the effect of B and SC. Sorry, it's the effect of new value C and SC, which I'm seeing out here. So again, this delay is really capturing kind of the delay of the combination logic. So it's just exaggerating the delays. Remember, input is coming from the outside, right? So we don't have any control over when transition from A to B or B to C are happening, right? They can happen unless the input is also coming from some circuit which is operating on the same clock. A, B, C may be changing at arbitrary times. But next state, in general, would, state in general would change at very, very quickly after the clock tick, right? Because the flip-flops are super fast. So what will happen is the next state is really a function of two things. It changes whenever state changes, and it changes whenever input changes. So in general, next state will see two changes, right? One is right after the clock tick, right? If I look at the sequence, clock comes, then that will cause state to change. And that will cause next state to change. In parallel, next state is also affected by any changes in input, right? So either the state change or input changes, that affects next state to change. And kind of we just try to exaggerate the delays just to kind of make the point that there is a delay in real circuits, both combination logic as well as the flip-flops. So that's what's going under the hood out here, that every clock tick, the flip-flops capture the next state, and then shortly thereafter, state changes, and then the effect of state and in compute the next state, which is then captured again in next clock tick, and the process keeps repeating all the time. And input is being changed asynchronously by the outside world, in the sense that input changes in input may or may not be aligned with the clock ticks. And when we say aligned, nothing is perfectly aligned, right? Real world has delays. So a signal which says it is changing on clock tick, what we really mean to say is it's being caused by the clock tick, but in reality, it will happen a short while after the clock tick. And this will also tell you one other thing, which we'll visit at the end of the course. What it also means is that next state should be ready before the next clock tick, right? If my combination logic is too slow, then next state may not be ready by the time the next clock tick comes. So there is a timing constraint out here that my combination logic has to be fast enough so that my new next state is ready before I get the next clock tick. And we'll delve into this thing in probably like very close to the end of the course. So now, with this in mind, right, that a sequential logic looks like this, I can basically now, we're going to focus on how do we analyze and design the behavior of these circuits. So let's consider a scenario where my state is 2 bits and my input is 1 bit. Okay, so n equal to 1 and s equal to 2, right? That's what we are looking at. N equal to 1 and s equal to 2. Just an example. Okay, so in this particular case, if I look at my combination logic, the input to it is in and state, and output from it are these two things, right? This is the output. And these are input to CL. So I can think of this whole thing as combination logic. It's a function with 3 bits of inputs and 3 bits of output. So it's really either you can say there are 3 functions, or you can say one function with 1 bit, another function with 2 bits, or you can just think of the whole thing as a 3-bit output function. Since inputs have 3 bits, so I will have 8 rows. So I can enumerate all possibilities of in and state. And then for each one of them, I can talk about what the output and what the next state is. So let's say that this truth table. So this is a dividing line, right? Between output columns and input columns. So let's say my table looked like this, right? It's just an example. So let's see what will happen. So firstly, let me ask you the following. Is this mealy or more? So remember, what was the definition of more versus mealy? Anyone?
I think more is only dependent on the next state.
Right. In more, no, it's only on the state, right? So
Yeah.
output is dependent only on the current state. So, and is independent of input, right? So what do you see out here? Is the output dependent only on state? Well, we can, what do you think? In this particular case, is out a function of just state or a function of in and state?
Shouldn't it be just mealy?
Yeah, it is mealy because of this little guy out here, right? I mean, what is happening is when state is 1, 0, in one case, output is 0, in the other case, output is 1. So it's not just a function of state, it is a mealy machine. Good. Okay. So that we had seen earlier. So in a more, a change in input alone should cause a change in the output only at the same clock cycle and not immediately. Okay, so we kind of talked about this. Okay. So now let's see how this machine will run. Okay. So we are going to go clock by clock in different rows. We have the state in and out. Okay. So let's say we start out in this clock edge number 0. Let's say the state registers had the value 0, 0. And input was 0. And since state is 0, 0, and input is 0, then output is 0, as you can see out here. So output is 0. And what is next state? Well, next state is 0, 0. So at the next clock tick, let me just write down next state also. Right, so next state was 0, 0 out here, right? 0, 0, okay, so 0, 0. And so this 0, 0 will go out, become the state for the next clock tick. But let's say now input is 1. So now we have 0, 0, 1. So 0, 0, 1. So we are in this row. Right? Input is 1 and state is 0, 0. So output is 0. But next state is 0, 1. So now, as you might guess, in the next clock tick, state becomes 0, 1, right? This goes out here. And let's say input remain unchanged, 1. So what will happen now? So 0, 1, 1, right? So state is 0, 1, input is 1. So we are in 1, 0, 1, right? This value here. And so next state becomes 1, 1.
Quick question.
Yeah.
Is next state solely determined by state, or is it determined by both like input and state?
Well, it's defined by this table, right?
Okay.
So,
Okay.
yeah. So whatever. So next state in general is going to be a function of both in and state.
Okay.
Okay. So in this particular case, for the second row, state was 0, 1, input was 1. So we were in the row out here, 1, 0, 1. So output is 0, which is what we see out here. And next state is 1, 1. And so 1, 1 will move to the state next time. And let's say input was 0 next time. Okay, outside world is doing whatever it is. So now we have 1, 1, and 0, which means we have to look for the row 0, 1, 1. Output is 0. And next state is 0, 1. So we'll get the next state 0, 1. And we'll hopefully you get the idea of what's happening, right? So every time we are computing two things, we're computing the output and we are computing the next state, and that next state feeds in, becomes the state for the next clock tick. And I'll let you play with this in your own time, but that's basically what is happening. Okay, so let's take another row number 5. So current state was 1, 1, input was 1. So we are in 1, 1, 1, output is 0, and next state is 1, 0. So 1, 0, and that's what we see out here. So that's what's going. So mentally, you can kind of repeatedly compute what this combination logic is doing and then see how the system will evolve over time. And then, as we discussed, this thing is a mealy machine because the output is not just a function of state, but is actually also a function of input, right? Particularly when the state is 1, 0, then depending upon whether input is 0 or 1, output is 0 or 1, right? So there is a dependence on the input. Okay, so now let's look at some useful examples. So let's say I want to design a circuit which at every clock tick is going to increment the output. So what I'm seeing on the output is a number, an unsigned number, and I want that number to increment every clock tick. And if it hits the max value, I want to circle back to 0. So this circuit that I have shown does that, right? I mean, if you think about it, so the state register has some n bits. I have an adder. So at every time it is taking whatever is the state value, right? This is the current state, n bit, and it's adding 1 to it. And then it's getting whatever is the current state plus 1. And then that becomes a new state, and the thing goes on. And the output, in this particular case, output just happens to be the same as current state, right? So it's a very, it's output equals to state. Okay, that's just a special case. So firstly, is this machine mealy or more?
I just had a question. So in this case, when you're doing this like first like addition, you have to initialize the state to something, right? You can't just be like
correct.
Okay.
Great point. I have not discussed that part, but for sequential systems, it's obvious. It has to be the case that all the states have to be initialized to something, because if they are initialized, like typically when registers power up or circuits power up, memory in general would be in some random state, right? Of course, that's unacceptable. So usually, well, not just usually, always, systems have a reset signal. And when the system powers up, we reset all the memory into a known state.
So if we are like implementing this in like Logisim, will Logisim automatically do it for us, or will we have to worry about like initializing state?
I don't quite remember whether Logisim. It's a little tricky thing. I think when Logisim really starts, it does put all registers to 0.
Okay.
The problem, though, is that oftentimes you are going to restart the circuit hot, as in you're not totally starting Logisim from fresh, in which case you would need to do a reset. I usually, so basically, I don't think you should rely on Logisim's inability to mimic the real world. In the real world, things, you have to assume that the things are starting in unknown state, and therefore you have to have an explicit reset signal. And if you look at the data sheets for whatever, a microcontroller or whatnot, you will see all these specs like after the power up for so many milliseconds, you must apply a reset signal, and so on and so forth. There are complicated specs around how to reset the circuit. Okay.
Okay.
Someone has to do that, yeah. But great point, yeah. I mean, otherwise, if you start from random stuff, you keep getting random stuff. Okay. Okay, so back to my question: is this mealy or more?
Is it mealy?
Why do you say that?
Because it relies on both the state, like the clock state, and it also relies on the input, like your previous number.
No, but remember, what is happening is, if I actually said earlier, right, output is equal to current state. So my output function only depends on the state. Next state function depends on both input and state, but output here is actually literally the simplest possible case, right? Output is state. So this is more, right? If I change the input here, its effect will be felt here, but not on output, right? Because there is a flip-flop sitting here. So another way of thinking about it is, for machine to be mealy, I should be able to go from input to output without going through a register or a flip-flop, right? If I'm going through a flip-flop, then there has to be then I'm more. Okay, in this particular case, I cannot go from here to here without going through this register.
So do you have to have like that immediate dependency where if you like
Yeah,
flip the
you
way
have to have
on
immediate
okay.
dependency, right? It
Okay.
literally has to be a function of in and input and end state. Okay. Okay. So obviously in this case we are using the state just to do some arithmetic. Counter obviously is a super useful whatever module. So we'll see more of it. Okay, let's look at this one. So there is some circuit where I obviously have a clock, rising edge. I have X as an input, U as an output. There is some state. We don't tell you what. What do you think? Is this circuit milli or more?
Wait, the top one is a different one and the bottom one is a different one, right?
What did you say? Yeah, that different.
I think the top one is more and the bottom one is milli, I think.
Yeah, you're right. So, okay. So the bottom one is milli because when X is like, look out here, if X is changing, U is changing immediately without waiting for a clock tick, right? Whereas in the top one, X was changing in the middle of the clock, there was no impact. X was changing in the middle of the clock, the impact happened only at the clock tick, right? So you can see, and likewise here, X changed in the middle, the impact happened at the clock tick. Okay, and then kind of similarly there. So bottom top one is more, bottom one is milli, right? So the point out here is that just by looking at the black box behavior, you can often infer the nature of the system. Okay, so okay, so I don't think I have my new slides out here, so just give me a moment. I'm going to upload the slides here. So that just a second. Let's do the following. Let's take a 5-minute break because I realize I didn't post it on Piazza also. So those of you who like to make notes and all, you'll have a bit of a problem. So let's take a 5-minute bio break while I post the new slide set on Piazza also. Okay, so we'll start at 3 minutes after 5. Okay, sorry about it. I totally forgot to post this stuff. Okay, we can resume. So sorry about the snafu. I also the link is both on Piazza and also on the chat. So hopefully you saw that. Okay, so what we saw thus far is that I can think of the sequential system in terms of this piece of combination logic, and which computes two things, right? Next state and output. And in general, output is a function of both the current state, or simply the state, and input. But the special case is that the output is a function only of the current state, in which case it's referred to as Moore machines or Moore finite state machine. And furthermore, one way of thinking about whether something is Mealy or Moore is whether you can, if you start from any of the input pins, can you go through the output pins without only through a combinational path? And if even one such path exists, right, if there is one input bit and one output bit, which you can go from the former to the latter without going through any register, then you have a Mealy machine. Okay, now, so I can, and then kind of we saw that truth table, which can help us analyze how this machine would behave over time. Now, just like for combinational logic, we had Boolean algebra to let us reason about how the combinational logic works. The question becomes, is there a similar mathematical framework in which I can talk about the behavior of these finite state machines and these sequential circuits? And that framework is called finite state machines, FSMs, finite state automata. If those of you are in computer science, maybe you have done a course by now where you may have encountered the concept of automata, and there are a whole sort of series of them. Finite state machines are kind of the bottom of a kind of hierarchy of computing machines of different complexity, right, and different expressiveness. Many of you perhaps have used regular expressions in your editors and some other software, and finite state machines are what are called as computing machines that can recognize regular expressions. Okay, so they're kind of very simple as computing machines go, but for our purposes, they are sufficient. So that's the mathematical framework. And we are going to look at that because what we can do is, just like given Boolean logic, we can go to Boolean expressions, we can go to combination logic, and given combination logic, we can give Boolean expressions. Likewise, given finite state machine description, we can go to a sequential digital logic, and given a sequential digital logic, we can go to finite state machines and finite state machine description, and then we can sort of work at that level. So let's talk about it. So we encountered this stuff previously. Okay, so in this module, we are going to look at how do we represent sequential circuits as these finite state machines, and then how can we design finite state machines. How can we convert them into circuits, right? So in some senses, given if I knew the truth table, or what we call as state table that we saw in the previous module, if we have that, then it's trivial to make a sequential circuit, right? We just slap some state registers and we're done. So the question really becomes, how do we go from this high-level description that I'll introduce to that truth table or state table that we talk about. So let's work to that. So in this lecture, in this module, we're going to look at what is the concept of FSM, what are the different type of FSMs, how to map them into sequential circuit, how can we optimize them, just like we learn about Karnaugh maps and how do we optimize combination logic. There is an equivalent concept out here. One of the things you have to worry about is, given a problem, how many bits of states do I need to store? Okay, because that affects the complexity of the hardware. And then I guess a point which one of you already brought out, which is how do we bring sequential circuit to a known state, right? I mean, otherwise than power up, they just start randomly. So let's talk about. So finite state machine is a mathematical concept, just like we had Boolean algebra. Finite state machine comes from more from CS theory side. So it's a mathematical model of sequential logic. It's used to help us design sequential logic circuits, and by the way, also software. So you can think of it as an abstract computing machine, which can be in one of finite number of states, right? And we talked about what a state. State means that given all that has transpired from t equal to 0 when the machine powered up, it is in I can think of it as being in one of the few possible things, right? So you can think of it as in my example of whether we have seen even number of ones or odd number of ones thus far. You can think of my system really is in two states. It has seen odd number of ones thus far or even number of ones thus far. So state is basically how many distinct categories of histories matter to me. At any given point in time, the system is in one state. Okay, so you can think of the state that the system is in is indicated by kind of what is in its memory, right? So if I have s bits of memory, then the maximum number of states that can exist is 2 to the power s, right? Because histories are being represented by those bits, and I have s bits, so I can represent 2 to the power s possibilities. So there are 2 to the power s possible states that exist. So now in this formalism, what we do is we represent states as nodes of a graph. Okay, so kind of idea is if I have one bit, then I can have 2 states, so I will have 2 nodes. Okay, so let's take this turnstile that we see in many places, right? So this turnstile has 2 states. It's either locked, right? You cannot walk through it, or it's unlocked, in which case you can walk through it. So you can say a system like this has 2 states, locked state and unlocked state. And then different actions by the external world cause the state to be changed. So in this particular case, there are 2 actions, right? We put a coin and we push. So if I'm in a locked state and some person comes and attempts to push it, I will stay in the locked state. And if I'm in the unlocked state, and if I push through it, then I'll go back to locked state. Moreover, if I'm in the locked state, I put a coin, I go to unlocked, and if I'm already unlocked and I put a coin, it will not have any effect. Or hopefully it's a smarter machine and it returns the coin. And that this symbol says, what am I starting out in? So this says that the machine, upon power up, will start out in locked state. This is power up, start. So the mathematical concept out here is that we are thinking of our system as residing in one of these states. Okay, and in general, there may be 2 to the power s states. And then I'm moving between these states based upon some action, some event being performed in the outside world, right? Some input changes or something, right? That's what we want. Thus far, we are not worrying about any clock and all out here, right? I mean, this is purely kind of the general view of a sequential system. right? The memory out here resides in the fact that if I have two states, I need to remember which state I am in, right? So therefore, I need, in this case, there are two states, so I need at least one bit. The act of moving from a state to another state, or even staying in the same state upon an action, those are called as transitions. Okay, so the nodes are the states, and the edges are the transition, and the annotation on the edges, like this coin, indicates what event or what action, what thing is, what is happening in the external world, which is affecting me and which is causing this stuff. Okay, we'll see a more formal kind of thing later on, but that's kind of the idea. So all the information about history really boils down to being in one of these two states or nodes of the graph. Okay, nothing else matters, right? I mean, in this particular case, there are many different sequences in which people may push and insert coins and whatnot. None of that matters. All that matters to the system is right now whether it's locked or unlocked. Okay, so that's the graph formalism. And then separately, we have seen this logic-based approach. And again, I've sort of drawn it yet another way. So imagine my state is being stored in the state memory, the state register, D flip-flops. And basically it is capturing the state, right? The current state. So that's the current state. And then my output logic, that's the part of my CL, part of my combination logic. It is going to use current state together with the input, right? So you see this general kind of arrow going out here, right? That computes the output. And next state logic, which is another combination logic, it uses the input and it uses the current state to compute what the next state is. If input didn't feed into output logic, then we would have a Moore machine, right? So in general, so we have two possibilities, Mealy and Moore, depending upon whether I have input affecting the output, feeding into output logic or not, right? Because if input feeds into output logic, that means I have a combinational path which goes like this to the output, right? Okay, so this is same. So this was a view we had in the previous slide set, and essentially the case I'm going to make is that the graph-based finite state machine that we just saw has a one-to-one correspondence with this kind of a hardware view of what is happening, and that's what we are going to build up, because then kind of the idea would be, faced with a problem, we'll work at that FSM graph level, but then we are going to implement this kind of next state output logic kind of thing. Okay. So we have seen this diagram, Moore and Mealy, so I'm going to skip that. Okay. Actually, just to make one other point. So more machines are machines, this figure we have seen, more machines are machines where output logic no longer depends on the input, right? It's only dependent on the current state there. So that's a Moore machine. If you look at this, it is clear that in case of a Moore machine, output is separated from the state, the output of the state vector, by some combination logic, right? But effect of input doesn't show up on the output immediately. It's always delayed by a clock. But this output logic in general is going to add some delay. So if you look at the Moore output, it is not going to happen immediately after a clock tick, but after a little bit of a delay, whatever the delay of this output logic is. Mealy machine, we have input feeding into the output logic, and therefore if input changes, the mealy output changes potentially immediately, right, or after a short delay. So this is mealy. So output depends both on current state, whatever is in the state memory, and on the input. There's a third type of machine, which is a very special case of Moore machine, where the output is a function only of the state. We saw one example of that. Anyone remembers from earlier today? We saw one finite state machine, one sequential system, where the output was a function only, literally output was state. No one does? Remember the counter?
So how is this different than Moore machine?
There is no combinational logic, right? So output literally is sum of the bits of the state. So the difference is, in Moore, you have this combinational logic. So output is separated from the state bits through some gates. So there will be some delay that can occur. So if someone was observing changes in the Moore output, they will happen after some delay that is defined by the combination logic out here. Whereas in a circuit like this, as soon as the output state bits change, so some of those state bits are feeding to the output and they are reflected immediately. Okay, so this ensures that output changes right at the clock edge. Okay,
There's no delay in this system.
Yeah, or much less delay is
Okay.
probably the right term, right? Whereas the previous one, there can be significant delays, and so this one has advantages in terms of like a very predictable behavior of when the output is changing. Okay, flip side is that it may require more state bits, okay, to make this magic happen. Okay, but it can always be done. Any system that you can do it. The previous two ways you can do it this way, but it has better properties in the sense that the delay from output, clock edge to output changing is as low as possible, right? Essentially, whatever is the tiny bit of delay that may exist in the flip-flops. Okay, so output is directly a function of some of the output bits are literally some of the state bits. Okay, then there is another version of the state machines. These are this is called clocked Mealy machine. In this case, what happens is, so this part is like a regular Mealy, but then what we do is we slap to it a register. Okay, so essentially. What we do is we take the output of the Mealy machine and then we feed it into a register, right? If the output was 1 bit, then just a flip-flop. If output was 10 bit, then a 10-bit register, and use the same clock and then take that output. So in this case, this is kind of like, it's often referred to as pipelining. Kind of the idea is that I'm delaying the output by 1 clock tick. It has the same property that output now is directly coming from a flip-flop. There is no intervening combinational logic, but I'm delaying the output of the Mealy machine. Okay, so very similar in terms of its electrical properties, that is output changes immediately on the clock tick here also, but it's just structured differently. Okay, yeah, this is really, so this too is a Moore machine, because if you think about it, I can think of this register and these two registers as really part of my state. And what is happening is some of the state, this part of the state is directly the output. So this too is called clocked Mealy, but it is really a Moore machine. Okay, because all that I'm doing is I'm drawing it so that my state register, state is really split into 2 places. Okay, so one way of thinking about these systems is all the registers in my system collectively constitute the memory I have. That's the state. And so this case also, while it is designed as if I took the Mealy machine and then put a register at its output, it's really a Moore machine. So, but kind of just looking at it, sometimes you might find it useful to think of it as a Mealy machine with a delay at the output. Right? Just remember, a flip-flop like this, a register like this, all it is doing is it's really taking whatever is coming on the input, and it waits until the next clock tick to reflect on the output, right? So you can think of it like it's kind of saying wait until the next clock tick for the output to change. So oftentimes one can think of it as kind of like a delay of some sort. Okay, so we have these two ways of thinking about our sequential systems. We can think of them in terms of the circuit, and we saw a variety of ways, or I can think of them in terms of my finite state graph, that node structure. So what is going on? What should I do? Like, I mean, how can we map between the two? So I'm going to make a bit of somewhat of a informal argument out here to see kind of how it works, right? So let's take kind of the generic case of as shown out here. Okay, so I have a next state logic, I have output logic, I have current state. This is just a Moore machine. Okay, so which state I am in, right? Which node in the graph I am in, that is really being captured by the state memory, right? So I'll have to have different possible bit patterns in the state memory are going to tell me which of the nodes I'm in. Okay, so now let's talk about what if I have some edge like this. I'm in a current state, and then I say if x is equal to 1, go to the upper next state, and if x is equal to 0, go to the lower next state. Let's say I have something like this, right, in my graph someplace, depending upon what input I'm getting from the outside, I'm moving to one or the other state. Literally, what is going to happen out here is that it is this logic, right? This part, if x equal to 1, go to this. If x equal to 0, go to this. That is really making me say something about my next state logic, right? So in the next state logic, what will happen is it will say if x equal to 1 and the current state is whatever is the bits representing the current state, then the next state is whatever are the bits representing this upper state, and vice versa, whatever is the lower one. So I can, given the hardware, I can kind of think of it in terms of, instead of that table, we can think in terms of how I am moving in that graph. So there's kind of a one-to-one correspondence literally out here. My graph tells me about what goes into the logic, and my logic tells me how the graph will look like. So you'll have to convince yourself it's kind of not, I mean, the mathematical, like one can rigorously prove that is the case also, but it's better to think about something like this intuitively, that these transitions together with the conditions on them are really indicating something about my next state logic. We have not talked about what the output logic is, so ignore that for the moment, but these annotations on the edges are really helping us define the combinational logic. So let's see how it sort of plays out. Okay, so let's take an example. Again, just to make the point that it is actually, okay. So let's say we had the graph as it was on the left-hand side. No, sorry, table as it was on the left side. So in this particular case, in and state are the inputs to the combinational logic, in combinational part of the sequential logic, and out and next state are the output, right? So this is my dividing line. Left is input, right is output. So looking at this, I see what are the states appearing: 0, 0, 0, 1, 1, 0, and 1, 1. So I can create nodes in my graph and give them the name 0, 0, 0, 1, 1, 1, and 1, 0. Just think of them as names of those nodes. Okay. Or if you prefer, you can say S0, state 0, state 1, state 3, state 2, whatever, right? So there are 4 states. And then if I'm in state 0, 0, 0, and input is 0, then next state is 0, 0. So if I'm in state 0, 0, and input is 0, then next state is the same state. So that is this edge. So this row is corresponding to this edge, right? Just saying, if I'm in 0, 0, stay in 0, 0. You see these notations like 0, like focus on this, like 0/0. This is condition, input condition. And this is output action. So what this is saying is, if input is 0, make this transition and set output to 0. And that's what we have out here, right? Input 0, output 0. Let's take a more interesting example. Let's say we take this guy. So it's saying, if I'm in state 0, 0, namely this node, next state is 0, 1. So that's this edge. I'm going to make this transition if input is 1. So that's what you see out here. And by the way, output is 0. So that's a 0 out here. Let's take another example. Let's say I'm in state 1, 1. And let's say I'm here. State 1, 1, and input is 1. So next state is 1, 0. So I'm in 1, 1. Next state is 1, 0. Input is 1. So that's why you see 1 out here. And output is 0. That's what you see output 0 out here. So it's a stylized way of representing what is happening in my table out here. And remember, this table, what we have, corresponds to the hardware. So what we have on the right hand side is our finite state machine graph. The only thing which sort of just remember is that 0, 0, 0, 1, 1, 1, 1, 0, they are corresponding to how the bits are in the state register, but you can also think of them as names of the state.
I had a question.
Yeah, go ahead.
It's probably an obvious question, but so far we've been seeing tables where the state has 2 bits, but there could be ones with just 1 bit, right?
Yes, depending on your hardware, right? Depending on your system. In this case, there are 4 states, so I need at least 2 bits.
Oh, okay.
Right, to represent them. But I could, my turnstile example was a 1-bit thing, and you can have the counter example. If I had a 10-bit counter, then I would need 10 bits of state, right? I mean, so a counter. If I were to let's say draw a 10-bit counter, right? Then I will have kind of the counter will go like this, right? Lots of states, and then circle back, right? That's what a counter will do. And if I have 10 bits, then how many states do I have in a counter, right? So a 10-bit counter will go 1024 states. So there will be 1024 states, right? So 0, 1 through 1024. So that depends on whatever system you have. There's nothing, these are just examples with few state bits in order to keep kind of things simple for you. But there is no limit on how many states and therefore how many state bits you can have. The only requirement is that any given system will have some finite number of bits. And like I mentioned, modern systems, like if you look at Apple's M4 processor, which they announced yesterday, it probably has, I don't know, hundreds of millions of state bits, and therefore possible number of states is 2 to the power that, so a huge number. Okay, so modern systems can have really an insanely large number of states. Any other question? So I guess the main point out here is whatever I can express in the world of hardware, I can express therefore in the world of this table, and there is an equivalent graph corresponding to it. Okay, I can go back and forth between them. Of course, our kind of desire is that we should think of the system in terms of this graph, because it's easier to figure out what the functionality is and then go all the way to hardware starting from that. And even this graph, maybe not something you want to draw and all, maybe there's some sort of a language which lets you write this graph. So this is the state, this is the state transition, and the annotation on it is input condition, output action. So let's take another example. This is just one more example. Okay. In this case, this is from a particular software called FISM. So if you just Google for it, it's a graphical software which lets you design or draw finite state machines. So I'm just captured from that. There is no standard for how you draw finite state machines. Okay, but they're kind of similar, but every tool and every community has like people just follow somewhat similar but not similar but not identical drawing conventions. Okay, so in this tool, again, nodes are represented by circle. States are given some plain English names so that someone looking at this graph can understand what is going on. So in this system, this is some sort of a handshake protocol. There are 4 states. There is a state called idle, there is a state called done, there is a state called read, there is a state called delay. It is to read stuff from a memory. I think it's a controller for handshaking with a memory. You see one circle has double lines, right? Double circle, and that indicates the start state. Previously, we had seen another notation for the start state where I had a black dot leading to that, but there are many different conventions. And then you see these transitions. Now in this tool, sometimes the transitions are independent of the input, right? In the sense that, sometimes the output is independent of the input. In particular, for a Moore machine, output depends only on the input. Only on the state. And so in that tool, in this tool, if it's a Moore type output, they just put it inside the circle. Okay, so it's basically saying whenever I'm in the idle state, make output RD and output DS to be 0. Okay, so this is a state machine where RD and DS are outputs. And there is a signal called go, right? So if you think of this system, it has clock, it has go coming in, it has RD going out, it has DS going out, and it has WS coming in. It has 2 inputs, WS and go, and 2 outputs. So it's basically saying, if I'm in the idle state, if not go is true, in other words, go is 0, then stay in the idle state. And by the way, while you are in the idle state, make sure RD is 0 and DS is 0. And then it's saying, if I'm in idle state and go is 1, then move to the state called read. And when you go to the read state, make RD equal to 1 and DS equal to 0. And then immediately, as a next clock tick, you move to the DLY state, right? So this is saying here you don't see any condition, right? There is no condition. They're saying unequivocally from read, go to delay, DLY. And by the way, in delay, make RD equal to 1, DS equal to 0. So it remains the same. So thus far, read and DLY kind of look similar thus far, but there's a difference, because in DLY, we look at the signal WS. We are saying if you are in DLY, and if WS is true, WS in this case stands for wait state, because it's saying keep waiting. So if that's the case, WS go back to read. So essentially the idea is as long as WS is high, we kind of spin between these two states. We basically stay in this cluster out here, but we stay in delay. Otherwise, if WS is 0, then from delay we exit, we go to a state called done. Right, so essentially the underlying hardware area is a CPU or some sort of system trying to access a memory. Memory is slow, so the memory kind of gives a signal called WS saying, hey, wait. Okay, go is probably coming from some user or some processor. Okay, so we do done, and when we go done, then we put RD equal to 0, so we are done, no need to access the memory anymore, and DS equal to 1. It's basically a signal which in this case goes to back to the memory saying, hey, I'm done reading, goodbye. And then after the done, we again unconditionally move to idle. Precisely what this thing is doing is not the issue, it's just an example. But what I wanted to convey was that we can design, like we can write complicated system behaviors in this particular manner, where given the inputs Go and WS, output RD and DS, and some sort of a behavior that would be described usually in plain English. So like your protocol or standard or your customer would say, this is what I want the system to do. I want it to stay, keep waiting until a go signal comes. When the go signal comes, then you should go and read the memory. But by the way, the memory may be slow. So as long as the memory keeps giving you a signal called WS, keep the read signal to the memory asserted, and then when it's out of it, get out of it, and so on and so forth. So typically there will be a plain English description of what we want the system to do. Your job as a architect is to take that plain English description and come up with this finite state machine. By the way, things like chatbots are pretty good at it, so you might want to give it a shot. Okay, in fact, I wouldn't be surprised if some of the chatbots can even draw diagrams like these. Okay, and then once we have diagrams like these, then going from here to the state table is a mechanical operation, and then from state table to hardware is another mechanical operation, mechanistic operation. So one can really, so the hard part really is from a natural language description, how to end up with a state diagram like this, and also to make sure that the state diagram is efficient. It doesn't have useless states, for example.
I had another question.
Sure.
In the case of unconditional jumps, that means that no matter what our input is, the memory is going to change.
Correct.
Oh, okay.
Yeah. So at that point, if my current state is done, then irrespective of what the input is, the next state is idle. Okay. So and we have two such edges out here of unconditional transition. Okay, what else? There are variations of these things. Okay, so like sometimes if you see out here, I have listed Go, but I didn't say anything out here. And so some of these, sometimes the convention is, remember, if I'm in this state and if Go is high, I'm going to read, but I didn't say what if Go is low. Kind of the idea is that the remaining edge implies Go is low. Okay, so sometimes we just allow for these kind of shortcuts, not always, and I think I frown upon it. Okay, and so but those are some conventions. Sometimes inside this particular tool, FISM, it also allows things like this. It says pre-RD, there's some other output called pre-RD equal to Go. This is actually a mealy thing, right? Because it's saying pre-RD output is directly dependent upon the input signal Go. So that is mealy machine. And then finally, yeah, don't worry about detail, but in this particular tool, it can also force, it can basically say make RD and DS to be state bits. Okay, part of the state vector. We'll not worry about it out here. Okay, and then finally, sometimes like you may have see a diagram like this, where all I have is I'm in idle if go to read, but I'm not even saying what happens if not go is true. In that case, even the loop is implied. Okay, that is basically we are saying there is an implied not go out here. These are all variations on kind of the idea that I can draw these things in graph like these, and different tools kind of give you different stuff. So over the past few years, I kind of wrote just for purposes of this course, I kind of wrote a simple tool which lets you design these things in terms of a graph, and then go all the way to a Logician implementation. So I'm going to talk about that at a later point sometime. But yeah, there are professional caliber tools. Sometimes instead of listing the output inside, we kind of list the output out here, right? We saw that earlier, right? I mean, so we can say go, and then we can say pre-RD equal to 1. So we are basically saying if go, take this transition, and pre-RD is 1, right? So it's essentially, this is implying a mealy thing, right? Because it's saying pre-RD is 1 if go is true. So there are, again, variety of things. There is an alternate representation of start state. So instead of double circle, I can also indicate start state in this way. So you might encounter in various places on websites and all that you look, different conventions. So I just wanted to expose you to that. Okay. Okay, so that's the FSM concept. Now let's talk about types of FSMs. So here by type, I don't mean mealy and more, right? I'm not talking about mealy and more sequential systems. I'm talking about what kind of FSMs functionalities exist. So this little bit comes from the way computer science theory organizes state machines. Okay, and very broadly, the kind of problems that we encounter, they can be thought of as one of these 3 types of state machines: acceptors, classifiers, and transducers. They kind of correspond to, you can think of them as application level functionality that gets realized, 3 broad categories. So let's talk about acceptors first. So they are, the idea behind these machines is that they are seeking to recognize patterns. Okay, so there's an input coming in, and they are on the lookout for some pattern in the input. And whenever the pattern is found in the input, then they go in, then they are supposed to indicate that to be the case. And in particular, like these would be kind of problems where saying, hey, here is a long string, and if you see successive pattern 1010 anywhere in the string, then the string passes. Okay, so it's more like, is the string acceptable or not? That's kind of the idea. But the acceptance criterion is based upon some sort of a pattern matching. So that's the broad category of problems. A lot of problems fall into this category, that we seek to look for a pattern in the input. So in general, so let's look at this machine. Okay, what do you think it is doing? Stare at it for a moment and see if any of you can figure out what's happening here. So we start in the start state, and output is 0. So now try to see what is this thing trying to do.
It is trying to match the text UCLA, I think.
Yeah, it's trying to match the text UCLA. So its default thing is start UCLA, right? So it's moving if n is equal to u, and then n equals c. Okay, anytime it fails, it kind of goes back. So it's saying if n is not u, and it's not $, in this case is end of string. Okay, so and we have not reached the end of the string, then go back to the start, and so on and so forth. If I encounter the end of the string $, then I failed, the string fails to pass, and so we keep the output to be 0. And then if I see UC, and then after C, if I get a U, then I go back to the state. Otherwise, I go back to start and see how I've given the name states names like start. I have found a U, I have found a C. So found C means I have found U and C, right? L, found L, the state called found L means I have seen U, C, and L in succession. And then, of course, if I get an A after that, then it is success. And then once we reach the success state, it doesn't matter because all you asked me to do was to see if the string has a UCLA. It may have multiple UCLAs, but that I don't care about it, right? So this is the many problems. Like this is obviously kind of a made up example, but in real world, I mean, setting, it could be that I'm looking for a particular pattern of input to indicate the outside world is doing something, right? I mean, so there's a category of problems where I look for temporal patterns in the input. Okay, patterns could be very complicated. It could say, if you see a U followed by any other letters, then a C followed by any other letters, and then an L, and followed by any other letters, and then an A, even that is okay. They don't have to be consecutive, right? I mean, so there could be a variety of patterns that one may define, but common to them is there is a pattern, and then if the input has that pattern, then the string passes, otherwise it fails. Okay, yeah, that's the setting out here. Okay, so those are called acceptors, accepting a string or passing or failing a string, passing or failing an input, right? Also in this example, my input was binary, but more generally it could be anything. I may be getting a sequence of 8-bit 2's complement numbers, and the pattern I'm looking for is 3 or more negative numbers in a row, for example. Right, I mean, so it could be could be more general like that, right? So okay, so accepting state, rejecting state. What does this machine do? You already answered. It looks for UCLA. So what happens if the inputs are USC? So what will we do? Well, UCLA and USC have the U as common. So kind of when we are in start state, we get a U, we go to the same found U, but then we will bifurcate, right? We have 3 possibilities. We get a C, or we get 4 possibilities. We get a C, or we get an S, or we get a $sign, end of string, or we get something else, right? So you will have 4-way sort of fork, okay? So those are acceptors. There's a generalization of acceptors called classifiers. So in acceptors, we were only doing pass and fail. But more generally, I may want to think of, I'm getting inputs and I want to categorize them. I want to put them into one of K categories. So the UCLA, USC example is like that, right? I have UCLA or USC or nothing. But it could be more general. I'm getting, I give you a video and I want you to tell me whether it's a video of baseball game or video of soccer game or video of whatever, cricket or video of something else, right? I mean, so this is what machine learning systems do, right? They take a sequence and then they classify. So classification in that sense. So classifiers are just, you can think of that generalization of acceptors, except that now we have more than 2 categories, not just pass fail, but really multiple possible categories. And except now the thing is, this what we have out here is kind of the view which is more abstract. There is of course a hardware version of it, right? Somehow I have to tell the outside world, hey, I had a match, or so usually in hardware versions of this, or even software versions of it, there would be some additional signal called ready or something like that, some sort of a flag signal which will say, hey, there is a hit. Okay, and in case of and then the output would indicate whether it's a pass fail or what category it is, right? So the N in case of classifier is just 1 bit. In case of an acceptor, in case of classifier is more than 1 bit. In case of acceptor, just 1 bit. Okay, and then input may sometimes be have some sort of a special symbol indicating like there may be multiple inputs coming back to back. So the dollar or some sort of a special symbol may act as a separator between back-to-back inputs. So there could be kind of other baggage around it, but fundamentally under the hood, what these things are really doing is this kind of a categorization, either two categories or more than two categories. Okay. So I'm going to stop out here. We're going to pick up this thread next time. But as I mentioned at the beginning, after a short 10-minute bio break and all, at 6, I'm going to be back out here and go over the design assignment. Again, I'll record it, so no need to attend if you don't wish to attend, but you might find it useful. So if so, just hang around. I'm going to be terminating this Zoom session, so you'll have to re-log in. This is just so that I can get the recording going. Okay. Okay, so bye for now.